And hello, everyone. Welcome back to the online causal inference seminar. We are very pleased today to welcome Linbo Wang from the University of Toronto, who will be talking to us about causal inference on distribution functions. In the Q&A, Linbo has one of his co-authors, Zhenghua Lin from the National University of Singapore. So he will be answering questions. After Linbo's talk, we'll have a discussion from Hongtu from the University of North Carolina at Chapel Hill. Questions today will be handled by Dominic, so I'm switching over to him now.
Thanks, Georgia. So there are two ways to participate today. The first one is you can just submit your question in Q&A. Also, Linbo will stop from time to time. So when that happens, you can just raise your hand and we will unmute some of you so you can ask your directions directly. Yeah, please keep in mind that the talk will be recorded and maybe posted online. Okay, thank you. Yeah, Linbo, the stage is yours.
Okay, let me share screen. Can you see my screen okay?
Yes.
Great. So thank you very much for the opportunities to speak here. I think this has been a wonderful seminar series and I have thoroughly enjoyed it. So today I'm going to talk about how to make causal inference on distribution functions. So this is based on joint work with my colleague Zhenghua Lin from National University of Singapore, who is in Q&A with us today, and my colleague Han at the University of Toronto. So the motivation for this work is that so far I think most work, if not all the work in causal inference, has focused on how to make causal inference with observations that can be summarized by, say, a number or a vector. But in many modern data applications, we do not simply observe just one or several numbers for individual or observational unit. But instead, we might be observing a complex data object that can only be summarized by a distribution function. For example, in computer vision, the observations here we have are images. And we know that image is more than just a bunch of zeros and ones. Right? There's an underlying structure in the image that will allow humans to understand the meaning of the image. And this structure, turns out, can be best summarized using a distribution function. Or for example, in microbiome studies, we might be observing a different DNA sequence for a sample. And again, a DNA sequence is much more than just the number of ATCGs in the sequence. And the structure of DNA sequence contains crucial information for biologists to understand how this DNA works. And in phylogenetics, there is also a standard approach to represent the DNA sequence as a distribution on a reference phylogenetic tree. So it's a third example, which I'm going to focus on today. In applications like wearable device or climate change, instead of observing a single number for an observation unit, we might be observing a time series for each participant in a study. So one way to summarize the information in this time series is to use a distribution function. And in fact, in response to these challenges from modern data sets, there's an emerging field called statistical optimal transport. And this is becoming very popular in the statistics and the machine learning community. So what I try to discuss in this talk is, can we make causal inference for data objects that are represented by distribution functions? So as we learn in causal inference 101, the most important question, and sometimes I think the most tricky question, is how to define the causal effects of interest. A key challenge for defining the causal effect is that our definition of the causal effect needs to be interpretable so that practitioners can understand the meaning of these causal effects. But at the same time, we should also be able to develop methods to identify and estimate this kind of causal effects. So to keep things simple in this talk, I will only talk about how to make causal inference with a one-dimensional distribution function. So just to make my discussion a little bit more concrete, maybe we were interested in the causal question, what's the causal effect of getting married on your physical intensity level? And we're going to answer this question using data from the National Health and Examination Survey. So in this survey, the participants were asked to wear a wearable device called Actigraph 7164 during all non-sleeping hours for 7 consecutive days. So this particular device was placed on an elastic belt. And each participant was asked to wear this device on their right hip all the time, except when they go to bed or when they need to, say, take a shower or they need to swim, because this thing is not waterproof. So here's the data we have from this device from a 7-day period. So I just randomly picked 2 individuals from the data set. So you can see that on the x-axis, we have a total of 10,080 minutes. And on the y-axis, we have their physical intensity levels. And the gap between these the black histograms will be the time when they go to bed. So one thing you will notice, if you look at this data carefully enough, is that different people will have different circadian rhythms. Right? For example, on the right, you will see an individual who sort of wake up and sleep, wake up and sleep. They repeat this very regular pattern for 7 days. But on the left-hand side, this guy has a much more chaotic schedule. Right? For example, here, I think they stay awake for 48 hours straight. But remember, our goal is to estimate the causal effect on the physical intensity levels. Right? So these circadian rhythms are nuisance for our purpose. So to get rid of the effects of the circadian rhythms, we are going to transform our raw data into these distribution functions. So you can see that on this graph, you can only see what's the distributions of their physical intensity levels, but we no longer have their circadian rhythms here. And we're going to compare these distribution functions between the married and the unmarried groups. Okay, just to quickly summarize what I've been talking about so far. So I have a binary exposure A, so 0 for unmarried and 1 for married. And my outcome Y is a random distribution function that's mapping from an interval 1 to 1000 to 0 and 1. And I'm going to adjust, also going to account for potential confounders such as age and gender. So my goal, mathematically speaking, is to estimate the causal effect of A on Y while also controlling for this confounders X. So I hope the setup is clear. So I'm going to focus, have my discussions under the very popular classical framework of potential outcomes. Okay, so I will use Y parenthesis A to denote the potential outcomes Y under exposure little a. And we know in the classical settings, the individual causal effect is just the contrast between yi1 and yi0, and the average causal effect is just the mean difference between the between y1 and y0, and this will equals to the average of the individual causal effects in the classical setting. But it turns out that one major problem we will run into when we study this kind of problem is how do we even define the causal effect if the outcome is a distribution function? So from definition of the average causal effect, so we can see that there are 2 steps in making this definition. In the first step, we take an average of the potential outcomes. In the second step, we take their contrast. So on the surface, it's very straightforward to just extend these definitions to distribution functions. But because distribution functions at the end of the day, they still takes value on the real line. And in particular, we know a distribution function takes value between 0 and 1. Right, so in principle, we can do this pointwise. We can just take the Euclidean average and the difference to extend this definition for distribution valued outcomes. But what you're going to see in a minute is that perhaps this is not so desirable. So indeed, we need a better definition of the causal effect if our outcome is indeed a distribution function. So I will talk about this in 2 steps. The first, I will talk about average, then I will talk about how to take a contrast. Maybe I will quickly stop to see if there's any questions about the setup here.
Currently, we don't have questions, but I just want to encourage the attendees again, if you have questions, please raise your hand or submit them to Q&A.
Okay, great. So then I'm going to do my business. I'm going to first talk about how to take the average of this distribution functions, or define the mean potential outcome. So if the outcomes are just numbers, are real numbers, then we all know how to take the averages, right? If we have two potential outcomes, let's say y1 is 1, y2 is 3, then we know the average is just 2. And you learn this in kindergarten. But now let's consider distribution functions. Okay, but we're going to consider a very special case of distribution functions. Okay, let's say our y1 is a distribution function, but it takes point mass at 1. So in other words, this will correspond to a random variable. It takes the value 1 100% of the time. And I have another distribution function y2. This point mass at 3 is correspond to a random variable that takes the value 3 100% of the time. So this will correspond to the usual case where this y1 and y2 are real numbers. So intuitively, we know this y bar should be a distribution function that takes the value 2 100% of the time, right? So that this is so that the people in kindergarten can agree with us. But we are going to see that if we just take the Euclidean averages of distribution functions, we're not going to get what we want. So here I plot the distribution functions for y1 and y2. Okay, the blue lines is the distribution function for y1. And you can see that because the y1 takes the value 1 100% of the time, so there's a jump from 0 to 1 at the value 1. And here the green line is the distribution function for y2, and because y2 takes the value 3 100% of the time, so you can see a jump at the number 3 from 0 to 1 here. So now let's see what happens if we just take the averages of these two distribution functions. What we get is this red dashed line over here, right? Where between 1 and 3, this will take the value 0.5. So what this distribution function corresponds to is a new random variable that takes the value 1 50% of the time and takes the value 3 50% of the time. Right? This is not what we want, right? Remember, we want the distribution function that takes the value 2 100% of the time. Right? So that our whatever definition we come up with distribution functions will reduce to the classical definition for real values. But this is not the case if we just take the simple Euclidean averages of these distribution functions. So here's a more complex, but perhaps more realistic examples. So on the left, here our original data is a bunch of images for the number 6. And in computer vision, there's a standard approach to transform these images into a one-dimensional distribution functions. So if we just take the Euclidean averages of these distribution functions, what you will get is the thing on the right, right? It basically just stack all the number 6 together, and then you lose all the structural informations in the original data, right? You can't get the number 6 from the image on the right. Right, so instead of using the simple Euclidean averages for distribution functions, so we're going to use an alternative notion of averages from optimal transport. So this optimal transport is a subject that studies what's the most efficient way to move between two piles of dirt. Or in our case, this will be what's the most efficient way to move between distribution functions. So using the language of optimal transport, we can have a definition of distance, which quantifies the similarity of P and Q. And then this distance will correspond to the minimum effort of moving from distribution P to a distribution Q. Right, where we're using the two Wasserstein distance, meaning that we assume the effort moving a unit from S to T is the distance squared. So with this definition of distance, we'll be able to define a notion of average. So this is a so-called Wasserstein barrier center. So this is a particular distribution that is closest to the individual distributions under the Wasserstein distance. Or mathematically speaking, this will be the distribution that minimize the the total Wasserstein distance. I think there should be a summation of I here to the individual distributions. So maybe let's make this discussion a little bit more concrete. I go back to our first example where we have y1 equals 1 and y2 equals 3. And recall that if we just take the simple averages of the distribution functions, the y bar will be a new distribution that takes 150% of time, 350% of time. Now let's calculate how much effort is needed to move from y1 to y bar. At 50% of time, we're moving from 1 to 1, so there's 0 effort needed. And 50% of time, we're moving from 1 to 3, so the distance 2 effort is 2 squared is 4. So on average, the effort of moving from y1 to y bar is 2. Because by symmetry, we know the effort of moving from y2 to y bar is also 2. Right, so the question is now, can we do better in terms of this distance? It turns out if we try to move y1 to delta 2, right? Delta 2 is what we want. It's a distribution that takes the value 2 100% of the time. So if we move the distribution from y1 to delta 2, because always 100% of time we're moving from 1 to 2, so distance is 1, so the effort we need is 1. Right? So this is half of the effort we need to move from y1 to y bar. And turns out this delta 2 is indeed the Wasserstein barrier center for under this special example. So in the second example of the image number 6, we can also see that this is our original data, and this is our Wasserstein barrier center for this bunch of the images number 6. You can see that clearly this Wasserstein barrier center is much better in terms of capturing the structural information in the images than the Euclidean averages. So this is our choice for taking the average of distribution functions is to use the Wasserstein barrier centers. So here we're going to use the usual notation mu1 to denote the Wasserstein barrier center of the y1, the mean potential outcome under treatment, and the mu0 to denote the Wasserstein barrier center of the distribution y0, the potential outcome under control. But remember here, this mu1 and mu0, they are still distributions, right? They're just the distributions that are closest to this potential outcomes, to this each of the individual potential outcomes. Okay, so now that we deal with how to take the mean, we still need to decide how are we going to compare these two distributions, mu1 and mu0. So again, the naive thing you can do here is to just take the simple difference between the two distributions, mu1 and mu0. I mean, this is something that you would do naively, and then this individual causal effect will be the difference between the two distributions, yi1 and yi0. But this simple contrast has some limitations. So first of all, I think this is not very interpretable. Right? We all know what's the meaning of a distribution function, but what's the meaning of the difference of two distribution functions? Right? Obviously, if you take a difference of two distribution functions, they're no longer distribution functions. So what are they exactly? And the second, I think, is quite troubling is that if you define the causal effect in this way, then this average causal effect delta will not be the average of the individual causal effects. So remember, we have this property for in the classical setting for the average causal effect. And this is particularly useful if we want to interpret this causal effect on an individual level. Right? Because for any given individual, they can say the expectation of the individual causal effect will be the same as the average causal effect. So they can sort of take the average causal effect and use that as approximation for the individual causal effect. But if you define a causal effect in this way, this is no longer true. So you can no longer take the average causal effect as an approximation to the individual causal effect. And this is true even if you estimate not the average causal effect if you estimate this causal effect conditional on some covariates, or you estimate a conditional causal effect, this still this will not hold. So here's something that I think is more promising than just taking the difference of distribution functions. Is instead we look at the difference in the quantiles. Okay, so in this case, the average causal effect is defined as the quantiles of the barycenters μ1 and μ0, and individual causal effects is defined as a difference in quantiles of yi1 and yi0. Okay, and what this quantity will measures, it will give you the average shift in quantiles. So this is a function. So all of these definitions, this ACE and individual causal effect, these are functions from 0, 1 to a real number. So say if you plug in 50% here for the ACE, then what this function will tell you is what's the average shift in the median intensity level. Right? If you plug in 90% here, what this tells you is what's the average shift in the 90% quantile of the distribution. So I think this is something that's that can be interpreted in a real study, and moreover, this average causal effect defined in this way, you can show that this is indeed the average of individual causal effects. So that this average causal effect, even though we define this at the population level, they still have an individual level interpretation. Maybe I think I will stop here to see if there's questions.
Yeah, we just have one question submitted to Q&A that you might want to answer. So
okay.
Just I think a general question, whether the first part is now whether you're critiquing point estimates, because yeah, generally you can always predict the distribution of y under an intervention x with idea algorithms and other methods.
Okay, so the question is if I'm critiquing the point estimate, because otherwise I can get a distribution of y.
You can always predict the probability of a given event under an intervention. Should I just read the question to you, maybe?
Yeah, okay. Yeah, I think no, right? Because this is a completely different setup, right? Here, in a classical setting, we are only observing a single number for a unit. So it's true that you can have a distribution of this single number, but still it's a distribution of a single number. But here the setup is we observe a distribution for each unit, and how can we define the causal effect in this setting? So I think this is a different question.
Perfect. I think also Emma just raised her hand, so she might have a question.
Yeah, I just have a short, I guess, question. Is this kind of look similar, or I guess it doesn't look similar, but so what I would think to do if I have two distributions and I'm trying to compare them is something like a Kolmogorov-Smirnov comparison with the empirical distributions, like the supremum over the difference. And I mean, this is similar, I guess, with the, so just wondering if you
yeah, so this Wasserstein distance is just a different way of defining distance between two distributions, right? And in this and actually in this one-dimensional case, you can show that this is just the L2 distance between the quantile distribution, distributions. So it's a different way, it's a different definition of the distance. And the reason that we use this particular definition of distance rather than say, there are infinitely many ways to define distance between two distributions, right? But the reason that we pick this particular one is because of this interpretation in terms of quantile functions, right? We can directly interpret what's the causal effect as the difference in quantiles of the distributions.
I see. Thanks, Linbo.
Okay. And also, as a bonus, I think this is another reason that we prefer this particular definition, is that we can estimate the average causal effect in a standard way. So, for example, in a standard setting, that's classical setting, if your y is a real number, then of course, there are many more methods to estimate the causal effect. I'm just picking 3 that are most popular or are very popular. The outcome regression, the inverse probability weighting, and the doubly robust estimation. I'm sure most people in the audience are familiar with these methods, but in case you are not, you can just think of this as a black box, right? Where your input, it takes the outcome y as the input, then you run through this black box and then output a causal effect estimate. So it turns out if you want to estimate the average causal effect in the distribution function case, you can use exactly the same functional. But instead, in your black box algorithm, instead of taking your original outcome y as the input, you take the quantile function y inverse as your input. Okay, then you can just run your machinery and you still get your causal effect estimate. And we are able to show that the causal effect estimate you obtain in this way still inherit all the nice properties you have in a classical case, such as this is consistent, this is asymptotic normal, and you still have double robustness, for example. And this is quite remarkable because it's not as trivial as it seems, because if you define your average causal effect, not in a quantile scale, but on the original distribution scale, then this is no longer true. For example, naively, you might want to estimate this mu1 or mu0 just plug in the distribution functions y dot into this G formula. But turns out this is not true. Okay, you cannot estimate your mean potential outcomes by directly plugging the G formula. What you can do is use the formulation here, plug in it on the quantile scale, get an estimate of the mu1 inverse. Then you take the inverse of this guy to estimate your mu1. Okay, so this is so I want to emphasize that this kind of results only hold if you do all these calculations on the quantile scale, but not on the original distribution scale. Okay, so I think so far all the story seems pretty good for people like me who are not very familiar with optimum transport. But people in optimal transport may just come up and say, wait, in optimal transport, there's a more natural way to define the causal effect between mu1 and mu0, right, which is using the Wasserstein distance. Right, the Wasserstein distance minimum effort that's needed to move between mu1 and mu0. Of course, for me, the first reaction is maybe this is not so interpretable, because if I'm not familiar with all this Wasserstein theory, then maybe I don't know what is Wasserstein distance. But it does come with a major benefit that if you believe the assumption that the nature or the treatment will works in the most efficient way, or in a way that involves the least effort to move between mu0 and mu1, then this Wasserstein distance will come with a map that not only tells you what's the size of the causal effect, but tells you exactly how the treatment works moving from mu0 to mu1, right? So it's much more information than just a single number or a single function. It tells you a sequence of paths of how you can how the treatment works from mu0 to mu1. And so let me be more specific. If the outcome is continuous, then the optimal way to move between two continuous distributions turns out is to move between their corresponding quantiles. Okay, so there's a so-called optimal transport map to move between mu1 and mu0, and this can be this optimal transport map is the mu1 inverse composite mu0. So this is the best. This is the most efficient way to move from mu0 to mu1. And if you believe that nature operates in this way, then this will tell you, this map will tell you how the treatment actually works. So right now, it seems like we have two competing definitions of the causal effect. Right, one is the difference in quantiles, which for many statisticians, I think this is very interpretable because we all know what quantiles is. And on the other hand, I think these experts in optimal transport might prefer that we use the optimal transform map between mu1 and mu0 to define this is a causal effect. We can call this a causal transform map. So this seems the one of them is more interpretable, but one of them seems to give you more information and aligns better with the, this spirit of optimal transform. But turns out that these two definitions can be unified under a single framework. Okay, so this is our formal definition of the average causal effect. We call this average causal effect map of A on Y. So this is defined as mu1 inverse minus mu0 inverse, the difference in quantiles, composite another distribution, another continuous distribution lambda, which we call this reference distribution. Okay, so correspondingly, we can have the individual causal effect map of A on Y, which is yi1 inverse composite lambda minus yi0 inverse composite lambda. So this is just our original difference in quantiles composite reference distribution lambda. And depending on the choice of the reference distribution lambda, this will give us different things that we might be interested in. For example, if we just take the lambda to be a uniform distribution on 0 and 1, so this is nothing, we get what I think is more interpretable is the difference in quantiles. And if you take the reference distribution to be mu0, then after some simple calculation, you can see that this average causal effect map is indeed the optimal transform map from mu0 to mu1 up to an identity function. And if you choose the reference distribution to yi0, then again, after a similar calculation, you can see that this individual causal effect function will correspond to the individual causal transform map up to an identity function. Okay, so there's some subtlety here I want to mention because in general, the population causal transform map will correspond to a different reference distribution than an individual causal transform map. So in general, the average or expectation of the individual causal transform map will not be the same as the population causal transform map because they correspond to different, they use different reference distributions. But if you define everything using average causal effect map, which I talked about on the previous slide, then we do have this correspondence between average causal effect map and individual causal effect map. Okay, now let me try to explain this in a context of our data application. Recall that we're interested in the causal effect of getting married on the physical intensity level. Right, so this is what the empirical distribution looks like for a random subject in the data set. So you can see that this is a concave function, meaning that so the derivatives of this distribution is always decreasing. Right, so what this means, the density of your activity level is concentrated at a very low level, right? Because as the density as the value for the intensity increases, the density will decrease. So we want to compare these distribution functions between the married and unmarried group. So in the data set, we have close to 3,000 individuals in each of these two groups. So here's a crude comparisons between these two groups without adjusting for any confounders. So you can see that the blue curve corresponds to the barycenter under the married group, and the black curve corresponds to the barycenter under the married group, and the blue curve corresponds to the barycenter under the unmarried group. So you can see this the married group is slightly larger, has a slightly larger physical intensity level than the unmarried group. But as we all know, in causal inference, this kind of true comparison is subject to confounding by, for example, age and gender. So now let's first see what, without all this talk today, what would the people, how would the people approach this problem in a standard fashion? So if we just proceed in a standard fashion, maybe you will summarize the distribution functions with their mean, right? For each individual, you'll get what's their mean physical intensity level. Then you will apply the standard causal effect estimator, for example, the doubly robust estimator. So this is the result you will get. You will estimate that the marriage will increase the average physical intensity level by 21.7 counts per minute, and with this confidence interval. So this is what you'll get in a standard analysis, but you can see that this is throwing out a lot of information. And I give you many distribution functions, but you just give me a number back. So here's the final analysis with this approach. So here I brought mu1 hat and mu0 hat. So again, mu1 hat is the blue curve, and mu0 hat is the blue curve. Here, so you can see that this is after adjusting for the confounders, age, and the gender. You can see that we still see a difference between these two curves. And although these two curves, the difference, you may think the difference is small on the distribution functions, but I can also use this plot to show you exactly what's the size of the treatment effect. So looking at the plot on the left here, so x-axis are the quantiles, and the y-axis are the size of the treatment effect. Right, for example, and this is the average causal effect map with a 95% confidence band. So for example, from this plot, you can see that getting married will increase your median intensity level. So if you have a 0.5 here, it will increase your median intensity level by about 20 units. And you can also see this for every quantile that you like. But another way to visualize this is to have the same plot, but on the scale of the, not on the quantile scale, but on the scale of the reference distribution mu0 hat. So what this plot can tell you is that if you start from, let's say this is maybe 100 counts per unit, then after getting married at the same quantile, you will get to about 120. So this is the same result as before, but representing this on a different scale. And this will correspond to choosing a different reference distribution. And if you believe, I mean, this is a big if, but if you believe that really the treatment works in the most efficient way, right? Then what this causal transport map will tell you is that exactly how the treatment works. So that what this causal transport map will tell you is that getting married will move the 200 CPM to 220 CPM. And it will move 400 CPM to 430 CPM, and move 800 CPM to I don't know, 815 CPM. So this is this is a lot more information than what you can get with a single number, but this will also comes with the assumption that the nature will works in a way that's most efficient. So I just want to finish with some quick discussions. So what's the added value provided by this kind of analysis compared to the standard analysis where you just summarize each of the observation by their mean, and then just use any standard machineries to get a causal effect. But I think what this tells you is how the treatment works on each of the quantile of the distribution. And I think this is particularly relevant for applications like, for example, climate change. But we might have reason to believe that human behaviors will make the summer even hotter and the winter even colder. So this is the effects on the tails of the distributions. But maybe because you make the summer hotter and you make the winter colder, then on average the temperature, you don't see as big change in the average temperature. But in fact, there's a big change in how livable these temperatures are. Right? So I think this is a final analysis in some sense that this will allow you to capture the effects not only on the averages, but also on the tails or on any of the quantiles. And you can only capture this kind of effects using the difference in quantiles, but not using the more familiar quantile treatment effects. So I want to point out this subtle difference between the more familiar quantile treatment effects versus the difference in quantiles. And this also relates to the earlier question about we can estimate the distributions, but for individual observations. So let's say our data will have 100 units, and for each unit we'll have 300 observations, right? And let's say when we take a definition, we know the potential outcomes yg1 and yg0. So in defining the quantile treatment effects, right? Remember in quantile treatment effects still defined in the classical setting, where each unit only contribute one observation, right? So easy way is to just take an average of these 300 potential outcomes, and you calculate a difference. So you can get the individual causal effects delta 1 to delta 100. So for each of the unit, you get a causal effect. Then you take, let's say, 99% quantile of these individual treatment effects. So what this is doing is it targets the extreme units in the population. Or in the example of climate change, this will target the particular cities that are most affected by this human behavior, maybe those cities that are most close to the coast or whatever. But this is in terms of their average outcome. You still compare them in terms of their average temperature, right? I think this is what people are talking about nowadays, right? In Paris deals, we talk about the average temperature. We try to control the average temperature increase within 1.5 or 2 Celsius, right? And we talk about how this goal is important for particular cities that are most vulnerable to climate change. But what we talk about here is something different. We talk about difference in quantiles, right? So here for each individual, we're using these 300 observations to estimate the distribution function. And then we take an average over this 100 units, and we compare this Wasserstein Berry centers in, let's say, 99% quantile. So this is targets the extreme values in the distributions or the tails of the distributions, but for an average unit in the population. So this will allow you to capture effects on the tails, but for average unit in the population. So I think there's a subtle difference between these two. And depending on the scientific goal, I think each of these two can be meaningful. And also, I think in some applications, this perspective from optimal transport will be useful because in some applications, this optimal transport map will be the actual path taken by the system to move from mu0 to mu1. For example, in some biological systems, people believe that nature will evolve in a way that that consumes the least energy. And what this translates to under this framework is they will move along this using this Wasserstein, using this optimal transport map. So in that case, under our framework, you can use a mu0 as a reference distribution to estimate average causal effect. Okay, I think I will stop here and happy to take any questions. The paper is on archive.
Thank you, Linbo. Thank you for your great presentation. They're very clear. We do have a couple of questions, but because we're quite on schedule, I want to make sure that the discussion has their time. So we are going to move over to discussion, and then if we have time in the end, we will ask you the questions that are on the chat. So if you don't mind, stop sharing your slides, Linbo, and we can move off to open discussion. So Hongtu, feel free to take over.
Can you share the screen for me?
You should be able to share your screen.
Whether you share them for me?
Okay, I'll share the screen. Just a minute. Can you see the slides?
Yeah, I can see my slides. Thank you. I think first I want to thank the organizer for the invitation. And it's my great honor to be here and to discuss the paper by the Linbo and 2 other authors. And could you go to the next slide? And I just want to summarize the method that they propose. And actually, in a nice paper, they propose a novel framework of causal effect for the outcomes from the Wasserstein space of the cumulative distance functions. And here Y is the random object, but here is CDF here or density functions in a curved space. And actually most of the other part is basically they develop a double robust estimators and associated asymptotic theory for the causal effect, okay? And then they apply the method to quantify the causal effects of the marriage on the physical activity patterns using the wearable device data, okay? And I do read their paper a few times, and I also interacted with Linbo on several other locations. Basically I go to, could you go to the next slide? I always, when I read the papers, and because I'm pretty familiar with this topic, and I have the 4 following questions, and basically I needed to discuss. The first one is basically what they considered, because for the density functions, for any 2 probability measures in a real space, and actually the Wasserstein distance, okay, because the U and the V are 2 probability measures, okay. The P is real numbers bigger than, and from the 1 to infinity, okay, for any numbers. And actually the Wasserstein distance and can be written as the LP distance between their inverse quantile functions, and in the integration of that, and from the 0, you integrate that the differences, and basically from 0 to 1, okay, for any P in the 1 to infinity, okay. And that's my first comment is for everything they presented in the papers. I think they focus on the Wasserstein's disk space for the P equal to 2, okay. I think the general results hold for the P greater than equals than 1, okay, because and for certain part of their discussions, it's very natural if you write that relationship out, and actually that's make the discussion much simpler, and in the paper, okay. And that's the first comments I want to give. The second one is, and there are another way to tackle these problems is you take a functional transformation of density functions, okay? And instead of just working on this Wasserstein distance kinds of things, but even though for this W2 space, everything calculation is easy, okay? But if you take the functional transformation of density functions, such as the log hazard transformation, okay, basically you map all the density functions to a linear functional space, like L2 space, something like that. And then you can easily do all these calculations by using a traditional approach in a certain way, okay? And without dealing with these kinds of Wasserstein distance space approach. That's because it's typically people are doing the manifold type of curved space stuff. There's a 2 group of people are doing that. One is basically do everything in the curved space. Another approach is basically I transform everything to another space, easy to handle it, and do it over there. How much you really gain by doing that? I know the interpretations are different, okay? But how much you really gain by doing this stuff? Okay, there's no consensus associated with that. And the third question I have a comment is, I know they focus on one-dimensional and basically the probability measures in the real life. But if you think about even you extend the same framework to R2s, you lose all the beautiful properties you have in R1 space. Okay, that's because the general results for the Wasserstein distance, that's only valid, that beautiful property is only valid in one dimension. You don't have that similar properties in the multivariate dimensions. That's basically my third question. My first question, why do we need to truncate the data between 1,000 to 1? Have you done any kinds of the sensitivity analysis associated with that? How much that will influence the final results? And also for the data analysis, I think personally, I would love to see more in-depth kinds of data analysis for that application. The kind of ones, I'm okay with that. You presented that differences, but I think if you add additional covariance insight, how does that kind of changes we could observe for the data analysis? That's basically the 4 questions I have for this paper. Thank you.
Thank you. Linbo, would you like to respond?
Sure. Okay. I would like to thank Hongtu for the very insightful and deep questions. So let me start from the first one. So I will first talk about the difference between LP and L2. So in principle, you are certainly right that we can, instead of using a 2 Wasserstein distance, we can use any p Wasserstein distance. But I think there's one key property that may not hold if we use a p Wasserstein distance, which is that, remember in the talk, I have the simple example at 1 to 3, then I want the barrier center to reduce to 2, right? And this will still be the case if you use a p Wasserstein distance, if we only have 2 observations, right? Because the LP average under 2 observations is always the arithmetic mean. But if we have more than 2 data points, right, only under L2 distance can we get back the usual average. If we use the LP distance, we're going to get a different average under the LP scale, but not under the L2 scale. And only the average under the L2 scale will correspond to the usual average. So I think this is why this is one major advantage why we use L2 distance in the paper. And I certainly agree that all these discussions can be made without reference to any of the Wasserstein stuff. Right? We can just define this as difference in quantiles, or as you right here, we don't even talk about the Wasserstein distance. We just use the L2 distance between the quantile functions. But I think that this perspective from a Wasserstein space will be most useful if, as I said towards the end, if we believe that the nature will operate in the most efficient way, then this optimal transport can not only give us the size of a treatment effect, but also how this treatment works or how the treatment moves from mu0 to mu1. So I think this is for the first one. And for the second one, yes, this is certainly right. There are many approaches. So log hazard is one example to map the Wasserstein space to a linear space. And in principle, once we after this transformation, once we map this Wasserstein space to a linear space, we can do our usual expectation and the extraction there, right? Everything we can define our causal effect in the usual sense because we can take expectation, we can take the difference. But I think one thing, there's a key difference between what we are trying to do here and what these people in manifolds and functional data analysis are doing is they are only interested in, they're mostly interested in estimation or the statistical properties of your estimator, right? So you can do this transformation to a nice space, do all your calculations, derive all the properties, and then transform it back to get the nice properties on your original scale. But here, one of our end product is this definition of the causal effect, right? So really, we want our causal effect to be interpretable. So if you say take the log hazard of the density function and define the causal effect there, or mathematically speaking, this is certainly true, but how can we interpret the causal effect? I think this is the key to why we choose this Wasserstein formulation. And this is also relates to Emma's previous comment that why don't we choose cumulative distance? I mean, there are just numerous ways to define the causal effect, but we're just trying to for one that will give us the most meaningful interpretation. And the third question is a great question, right? Certainly, we would like to extend this to a multivariate dimension, a distribution function. But there are some key challenges in the extension here. So you are certainly right, like our interpretation in terms of quantiles is only true for one-dimensional distributions. If you have multivariate dimensions, all this interpretation in terms of quantile functions will break down. And in fact, we cannot even use outcome regression to estimate the causal effect. So, so the extension to the multivariate case, I can say that we might still be able to get the optimal transport map, right? Because optimal transport theory will still works in a multivariate distribution case. So if you are lucky enough to in a setting, say in biology or in some settings where you believe that optimal transport map is how nature operates, then we can still interpret this using the optimal transport map. But you are absolutely right that we no longer have the interpretation in terms of the quantiles. So that's the bottleneck here. How to come up with a definition that still still has a nice interpretation for multivariate case. So the fourth question is on why we truncate the data between 1000 and 0 and 1. So actually we do two truncations, but for different reasons. So we remove all the values 0 because remember this device is not waterproof, right? So 0 can mean two things. It can either mean that this particular individual is sleeping, right? They are doing nothing but just sleeping, or they can be like they are swimming. Okay, they are actually doing a lot of exercise, but because this device unfortunately is not waterproof, so they have to take it off when they go to swim or when they take a shower. So 0 will mean very different activities in this particular data set. So this is due to the limitation of the technology. So so we remove this value 0. And for the truncation at 1000, I think this is because most data are concentrated at a region that's smaller or equal to 1000. So right now we're using a very naive approach. We're just using empirical distribution function to estimate the tail of the distribution. I mean, this is of course not very, this is not ideal, right? There are many methods that you can use to improve this estimation of distribution function at the tails, right? For example, you can make some parametric assumptions at the tail using extreme value theory, for example, right? You can make some more assumptions to better estimate the tails, and this is a very important thing for point out on this, because as I said towards the end, right, a lot of the benefit of this approach lies on the ability to detect causal effects at the tails of the distributions. So this is a great point that we need better ways to estimate the tails of the distribution, so that we don't need to do this naive truncation. But why we truncate here just because we're not using the most advanced technology in estimating the tails of the distribution. So I hope that this responds to all of the questions here.
Thank you.
Yeah, thank you.
Thanks. I think we still have a little bit of time to take maybe 2 short questions. Georgia, you had a question, right?
Yeah. Well, thank you, Linbo. And I really enjoyed both the presentation and the discussion, and I definitely want to read the paper now. I had a question with respect to kind of like your asymptotics. Are the asymptotics pointwise for each quantile? And like, do you think that there are assumptions that we could make on these like Wasserstein barycenter that would allow us to estimate it consistently and like asymptotically normal as a function instead of just pointwise?
Thank you. This is an easy question. Our result is it's a Gaussian process. So this is for the entire function.
Oh, okay, that's awesome.
Yeah. So instead of proving this is converged to a Gaussian distribution, we prove this converged to a Gaussian process.
Okay, can I ask one more question, Dominic?
Okay.
So for your double robustness, then, like, do you need to, is there, I guess, like anything that is doubly robust, like, oh, I have to only specify the quantile correctly, the functional form of the quantile distribution at the median in order to get consistency at the median, or do you need correct specification of the whole function to get consistency at each individual point? Does that make sense?
Yes. So if you're just interested about say the value of a function at a particular point, right? Yes, you just need the formulation to hold for that particular point. And indeed, in fact, this is the classical result. You don't even need our theory to prove that. So you can you can summarize each of the distribution using the median thing, right? Then this is a classical doubly robust stuff. Your classical regression model holds for that particular point. Yeah.
I think Jingwang, you also had some questions. Do you want to?
Oh, I guess it's quite related to what you said. Just one small question is whether you have any convergence rates or distributional results on the average causal effect in terms of the distribution.
Yes, they converge to the Gaussian process root and rate. So
Okay.
at the same rate. So the only missing part we have right now, and I hope any experts can help us, is how to get the local semi-parametric efficiency. We are able to show that this is asymptotic normal with the usual rate, and we believe that this is achieve the semi-parametric efficiency bound, but yeah, right now we don't have a theory for that.
Okay, I guess the definition of semi-parametric efficiency is not entirely clear.
Right. We need to first extend what it means for semi-parametric efficient to
It's
the
not
functional
a semi-parametric
space.
problem anymore, actually.
Right.
Yeah. Okay.
Right. So we need to extend the whole framework to the functional space before we can prove this.
Sounds really interesting. Thank you.
Thank you.
All right, thank you, Linbo, and thank you, Zhenghua, for dealing with the Q&A, and thank you, Hongtu, for your discussion. Now I have some bad news. The online causal inference seminar is taking a break next week for American Thanksgiving, but we are returning on November 30th. Thomas Richardson from, I guess I forgot from University of Washington, will be giving a talk on single world intervention graphs, a simple framework for unifying graphs and potential outcomes with applications to mediation analysis. We hope to see you there.
Right, thank you.
Thank you. This was very nice.
Thank you.
Maybe someone can stop the recording.
Yes, I can.